Hi, welcome to the Olympiad geometry. Let's continue our study. So today I'm going to talk about a problem from the audience. I think as he mentioned, this is a problem from Usamo 2024, I think. Okay. So the audience comments asking me when will we continue our hard problem solving. I think the basic idea is that I'm going to finish the geometry treasure, which is extremely useful as a foundation. So I know I already made lots of videos about the foundation of the Olympiad geometry. But the problem is that once you know more about the theorems, you basically open your mind, and it's like you are standing on a giant. So I think that's very, very useful. So and basically there are lots of difficult problems associated with these theorems itself are very difficult sometimes. So I want to focus on the geometry treasure first, and then I'll make lots of time to make videos on the transformation, right? That's a very, very big topic. For the hard problem, I think you guys can always find difficult problems, and just please send it to me if you want me to make a video, and we can discuss about this in a video and show you how I solve the problem, show you how I try to approach the solution. Okay, that's it. Let's look at today's problem. Let H be the orthocenter of an acute triangle ABC. Let F be the foot of altitude from C to AB. Let P be the reflection of H across the BC. Right, this you should have a ring in your head. We already know lots of the properties of this. I'm not going to repeatedly prove it, so I'll just use it. Suppose that the circumcircle of triangle AFP intersects line BC at two distinct points x and y. Prove Cx equals to Cy. So for these problems, let's just draw the circle first, right? We want to have a circumcircle of the triangle ABC. It's easier to draw the circle first. Okay, that's our circumcircle, and we have the acute triangle here. Call it ABC. Notice that in the past we already proved that if I just let's find the orthocenter first. Right, this is orthocenter H. If I just connect the AH and extend it, the AH meets the circumcircle on a point, and we know this point and H are symmetrical to the BC, which means in this problem, we want to find the point P. That is a reflection of H across BC, which means P is on the circumcircle of triangle ABC. Okay, and suppose that the circumcircle of triangle AFP, right? CF is F be the foot of altitude from C to AB. So CF is altitude, and we want to find the circumcircle of triangle AFP. Right, let's just draw it. So it will be very, very something like this. something like this. Okay, now we have our circumcircle of triangle AFP. And we know that this circumcircle intersects a line BC. This is a line BC at two distinct points, x and y. So let's call this as x and call this as y. Then we want to prove that Cx equals to Cy. Okay, let's just look at the figure and repeat the problem again. Basically, the problem is saying that in the triangle ABC, we find the auxiliary center and we find the altitude CF, and we extend the AH, meet the circumcircle of triangle ABC on point P, and then we connect FP, and we find the circumcircle of triangle AFP, and this AFP, the circumcircle of triangle AFP meets the BC line on x and y. We want to prove that Cx equals to Cy. Just look at this, you can think this might be a difficult problem, right? Because we want to find Cx equals to Cy. So sometimes it would be easy to find if we can find the center of the circumcircle of the triangle AFP, and then we connect the center to C. We prove that the center of the circle, let's call it O prime, for example, O prime C would be perpendicular to XY. Then we can directly prove that Cx equal to Cy, right? But just think about this O, it's kind of unrelated to other points, right? Which means this is not a good method. Then what we have else? We have, let's just think about that if Cx equals to Cy. That means if Cx equals to Cy and we extend AC meets the circumcircle of the triangle AFP on a point, let's call it D, right? If Cx equals to Cy, then we know that we already know that Cx times Cy, we already know that Cx times Cy equals to AC times CD, right? And if Cx equals to Cy, we just need to prove that AC times CD equals to Cx squared, right? If Cx equals to Cy, we just need to prove that Cx squared equals to AC times CD. But AC times CD is difficult to find, right? Just because AC times CD is a power of C to the circle AFP, which we don't have any more information about it. Now we can think of another way. How did we find this point X and this point Y? This point X is intersection point of the circle AFP and line BC, which means AFXP are cyclic. Of course, it sounds like a redundant statement, but let's just, we are trying to solve the problem, right? So let's just do the connection of the XF and XP. So all we can get here looks like nothing, right? Just because we want to find the Cx, we want to find the relation of AC, and we want to find the relation of CD. So it's actually giving us a little hint that just look at the format of this one. So AC times CD equals to CX squared. That looks very, very similar to the case that two triangles are similar, right? And for example, if we have the triangle ABCD here, if the triangle ABC is similar to triangle CBD, right? If these two triangles are similar, that means we have, means we have DB to BC equals to BC to AB, right? Which means we have DB times AB equals to BC squared, right? It looks like this one, which means we want to find the two triangles. Remember that we want to prove this one, right? We want to prove it, which means if we can find two triangles, has a AC, has a CD, and they are equal to these two triangles are similar, then we can have this equation directly, right? Which means we need to find the triangle that include the CX and AC, which means we already get one triangle here. It is ACX. So we're looking for another triangle that is similar to triangle ACX. This triangle should be XC and CD, but you know, the CD is already out of the triangle AXC, which means it's impossible to directly use the triangle XCD, right? But in the figure, we only have one point here. Let's call it E. It's inside the triangle ABC. And directly, you look at the figure, it looks like these two might be the same, right? Just a brainstorm, if they are the same, then that means EC equals to CD, XC equals to CY, which means XEYD is a parallelogram. If that is true, then we know CD, right? CD times AC equals to EC times AC, which directly be triangle XEC is similar to triangle XAC. Now the problem is turned to this one. So if we connect XE, we connect YD, we connect XD, and we connect EY. Right, we connect these lines. The question is, can we prove that XEYD is a parallelogram? Is that true? We don't know, right? That's what we think of in the real exam. Whether XEYD is a parallelogram, we don't know. Let's try to prove it. If we want to prove that XEYD is a parallelogram, it's obvious. Y is a point that outside of the triangle ABC, which we know nearly nothing about it. Which means we can't use anything like, to prove that a quadrilateral to be a parallelogram, we need some kind of cases that like opposite sides are equal, right? We cannot use that just because Y is a point that we cannot difficult to associate with other point to get the length of the side. But it's easier to get the angles, right? Just because we have two circles here, which is a strong hint that we should use a way of proving parallel lines to prove that XEYD is a parallelogram. So let's consider about this. If we want to prove XE is in parallel with YD, right? We want to prove this. That means we want to prove angle XED equals to angle EDY, or angle XYD equals to angle EXC, right? If we want to prove that these two lines are in parallel, we can use that if angle XYD equals to angle EXY. And we already know that angle XYD equals to angle XAD, right? We know that angle XYD equals to angle XAD. Which means we just need to prove angle EXC equals to angle XAD is XAC, right? We just need to prove this one. What's the benefit of proving this one? Basically, we constrain our problem just in the circle ABC, right? That's a simplification of the problem. So now we want to prove that angle EXC equals to angle XAC, which means they have in the triangle XEC and triangle AXC, they have the common angle XCE, right? Which means we just need to prove triangle C, triangle CXE is similar to triangle CAX. We just need to prove this one, which means we just need to prove that CE to CX equals to CX to AC. You may ask, we already talk about this, right? Why we just like a circling here? It's just because when we have a gas, we need to restart from this gas, right? Okay, now we want to prove that CE to CX equals to CX to AC, right? Which means we want to prove that CX squared equals to CE times AC. We want to prove this one, right? We want to prove CX squared equals to CE times AC, which is CA. So CE times CA, because angle BEA is 90 degrees, angle CFA is 90 degrees. We know that AFHE are cyclic, which means CE times CA equals to CH times CF, which means we just need to prove CX squared equals to CH times CF. Right, we just need to prove CX squared equals to CH times CF, which means if I connect XH, we just need to prove that triangle XCH, right, triangle CXH is similar to triangle CFX. right? If this is true, then CX to CH equals to CF to CX, right? So now we want to prove that a triangle CXH is similar to triangle CFX. We know for these two triangles, they already have a common angle XCH or FCX, right? They already have this common angle. So now we just need to prove that angle XHC equals to angle FXC, right? We just need to prove angle XHC equals to angle FXC. Now it's very, very critical. Just because we know we are on the right path, because we finally find the angle we are trying to use, the angle XHC. Why I say it's a very critical moment? Just because when we want to use the angle XHC, we're actually using the problem set that P is a symmetrical of the point H, which is a good sign that we are using the problem set, which means we're on the right path. Okay, now we connect CP. Because angle XHC equals to angle XPC, which means we just need to prove angle XPC equals to angle FXC, right? And look at the angle XPC. Angle XPC equals to angle XPA plus angle APC. Right, that is angle XPC. And for the angle XPA, because AXPY are cyclic. So if we connect AY here, we know that angle XPA equals to angle XYA. Right, so it equals to XYA plus. For the angle APC, because ABPC are cyclic, angle APC equals to angle ABC. Which means we're trying to add the angle XYA and angle ABC. It equals to 180 degree minus angle BAY. Right? It equals to 180 degree minus angle BAY. And remember, we want to prove that angle XPC equals to angle FXC. Angle FXC equals to angle FXC equals to 180 degree minus angle BXF. Right, now we want to prove that angle BXF equals to angle BAY. Angle BXF equals to angle BAY. And it is obvious just because FXYA are cyclic, right? So this angle equals to this one. For here, we just know that it is true that triangle CXH is similar to triangle CFX, right? Because this angle equals to this one. So these two triangles are similar, which means the CH times CF equals to CX squared, which means CE times CA equals to CX squared. Right? So we get CX times CX squared equals to CE times CA. Right, so we just find the relation of CX that we just proved cx squared equals to ce times ca. Then the problem would be easier. We just need to prove that cy squared equals to ce times ca as well, right? We just need to prove this one. And if it is true, that means we just need to prove, right? We just need to prove this one, and it equivalent to prove that cy squared equals to ch times cf, right? Which means we just need to prove that triangle YCH is similar to triangle right, we just need to prove that triangle YCH is similar to triangle FCY. Right? So CY to CH equals to FC to CY, right? So we want to prove that these two triangles are equal. And we already know they are sharing the angle HCY. So we just need to prove angle CHY equals to angle FYC or angle CYH equals to angle CFY. Right? So you can choose which one is easier. I would say this one would be easier, right? Just because angle FYC equals to angle FYX, right? Angle FYC equals to angle FYX, which equals to angle FPX or angle FAX. We don't know which one we're going to use, but I'll just write all of them, right? The angle FYC equals to angle FYX, which equals to angle FPX equals to angle FAX, right? And for the angle CHY, for the angle CHY, we know that because H and P are symmetrical point, right? So angle CHY equals to angle CPY. Right? So basically we want to prove that angle CPY equals to angle FPX. Right, we want to prove that angle CPY, this one, equals to the angle this is CPY equals to angle FPX. FPX. We want to prove that this one equals to this one. Now just look at these angles. We know that the angle CYP equals to angle XFP. Right? The angle CYP reference to the chord XP, which means, that angle XFP equals to angle CYP. So this angle equals to this one, which means we want to prove that angle CHY equals to, we want to prove that angle CPY equals to angle FPX, equivalent to just prove that the triangle FXP is similar to triangle YCP, right? Okay, let me write it here. Just equivalent to prove that triangle FXP is similar to triangle YCP. Right, we just need to prove this one. So for here, look at this angle, the angle PCY. It equals to the angle PCY equals to 180 degree minus angle XCP equals to 180 degree minus angle BCP, right? And so it equals to 180 degree minus angle BCP. And we know that angle BCP equals to angle BAP. Right? Angle BCP here equals to angle BAP. And we know AFXP are cyclic, which means 180 degree minus angle BAP, that is minus angle FAP, which is angle FXP. So it equals to angle FXP. Right? So it is saying that we just proved triangle FXP is similar to triangle YCP, right? Because the angle CYP equals to angle XFP, and because angle PCY equals to angle FXP, right? That means the triangle CPY is similar to triangle XPF, which means angle XPF equals to angle CPY, right? So these two angles are equal, which means we come back to here. We just proved CPY equals to FPX, which means we proved angle CHY equals to angle FYC equals to angle FYC. So we just proved that the triangle YCH is similar to triangle FCY, which means CY squared equals to CH times CF, right? So CY squared equals to CH times CF, which means CY equals to CX. Oh, I wrote it here. CY equals to CX. Right, we just prove it. And I want to stop here. Just look at this figure. We said at the very beginning, the thing that inside us is like, we want to prove that XEYD is a parallelogram. So is that really true? Right, we start from using YD, XE, and basically we relate it to XC squared equals to CE times CA. So is it still true that XEYD is a parallelogram? We just proved that XC equals to CY, right? It's actually related. So because we just proved that triangle CEY is similar to triangle triangle CEY is similar to triangle CYA, right? So that means this angle, the angle CEY equals to angle AYC. And angle AYC equals to angle ADX, which means the angle CEY equals to angle CDX, which means EY is in parallel with XD. And we just proved that triangle EXC is similar to triangle AXC, and we know that XE is in parallel with YD. So it is true that XEYD is a parallelogram, which means the diagonal XY and the diagonal ED bisect each other, which means not only CX equals to CY, but CE also equals to CD, right? CE equals to CD. I believe that in the problem set, they don't want to write CE equals to CD, right? Because that would be a super strong hint that you just need to prove XEYD as a parallelogram. But if they just hide this one, you need to figure it out. You need to figure it out that you want to prove XEYD as a parallelogram. That makes the problem a little harder. And I don't want to stop here either. Just look at this figure. We just proved that XPD, in the figure, it shows that XPDY are cyclic, right? In fact, XHEY are also cyclic. So I'll leave this to the audience. It's just a little more step, right? One step more. So I'll give the hint here. So if you connect to BP, you can actually find that triangle BXE is similar to triangle BPY. And the triangle BXH is similar to triangle BYH. Okay, all of these things you can explore. Okay, that's a problem for like USA Math Olympiad 2024. I do think this is a hard problem. I think the most critical part is that you have to figure out how to use your target, right? Your target is to prove that CX equals to CY, which is kind of unrelated from the figure because this C point is like arbitrary point. It's just from the triangle ABC. And you want to find that CX equals to CY. The first thing give you the hint is that you just need to prove that CX squared equals to CD times CA. Then it leads you to find another triangle inside the triangle AXC so that you can make CX squared, right? That's a break point. And if you can reach this break point, then I think the rest of the part would be not that hard for you. Okay, that's the problem from audience. So if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. See you in next one. Thank you.